Today we're looking at derivative control. We've already looked at proportional, integral, proportional, and integral together. And now we're looking at proportional and derivative together. The reason being is you can't have derivative on its own. It has to be proportional and derivative, or proportional, integral, and derivative. So, to start off, we're going to start off with proportional and derivative. Now, what does that look like for an equation? That is going to look like your V out is going to equal your bias times, plus your proportional output, which is proportional gain, times your error, times your direction, reverse acting or direct acting, plus, now here's where we start something new. We are going to go proportional gain times your derivative gain. In our case, it's TD on our controllers, okay? But in a lot of other places you'll see it, it'll be DG for derivative gain times your error over time. And then you also times that by the direction of your output, whether it's a direct acting or reverse acting. Now, error divided by your time is your ramp rate, okay? Notice if we have zero error, its derivative is going to be zero if we have no error. If we have no time, if it's instantaneous, then the time is going to be zero and there'll be no derivative. It has to be some kind of ramp rate. It can't be a steady state. Now we're going to look at that. Let's say that we have a proportional gain of 0.2, a derivative gain of 0.2. We are going to have a ramp rate of 200. Okay, so I'm just going to call this ramp rate.
Where is that TA?
That is TD. That's the way it is in our controller. Now, where do we get this ramp rate from? The ramp rate comes from when we have the process variable, and let's say the process variable started at 0. And what we're going to do to make this simple, to make it so that we can grasp it very quickly, is when the process variable increases, we have a ramp rate. We have an error over time, right? So in this case, let's say our error was 100% over 29.4 seconds. What do we have there? What's 100 divided by, that's seconds. We have to convert that into minutes. So it's basically 0.5 minutes. Always keeping that in mind, that time is in minutes. So 100 divided by 29.4. What is that? That should be 4.9 and, 0.49. 0.49 times, 100 divided by 0.49. Can somebody do that for me? 100 divided by 0.49. What does that give us? Equals 204. Okay. So, if we go from a process variable and we have a set point of 0, okay, so our set point is 0. Our process variable goes from 0 to 100% in 0.49 minutes, excuse me, or 29.4 seconds. Our output, our valve out, is currently at 100%, okay? That's our bias, is 100%. What derivative does is it acts against a ramp rate. Whenever it sees a ramp rate, it wants to, in reverse acting, counteract that ramp rate, okay? We're going to see that here. We have our bias of 100. So V out equals our bias of 100 plus our proportional gain of 0.2 times our error. Now, currently our error is 0, right? Sorry. Yes, currently our error is 0. So it's 0, our time is 0, our starting point will be 0. Okay? We're going to see that here. Proportional gain, 2. Our error, our set point, and our process variable at time 0 is 0. Our process variable minus our set point, 0 minus 0 equals 0. Times our direction, which we're in reverse acting, so it's minus 1. So that equals 0. Plus proportional gain, 0.2 times our derivative, 0.2 times our error. Our error is 0 and our time is 0 times our direction, which is minus 1. So that equals 0 plus 0 plus 100, which equals 100. So our starting point, if we start off and we start this ramp at the beginning, when things just start, we're at 100% output. Now, we start ramping. And as soon as we start ramping, right at 0.1 second, what's going to happen? We are going to have V out equals 100 plus our proportional gain times our error. Well, if it's 0.1, our error is still 0. It'd be like 0.01. Essentially nothing. Times minus 1 plus, now here's our derivative. This is where derivative kicks in. We have our proportional gain of 0.2 times our derivative gain of 0.2 times, now you could get very small numbers, or we could just take, if this is a linear ramp rate, we could just take the 100% divided by 0.49 and we get 204, okay? So we take our error over time, over the whole thing, to get our ramp rate. Okay, we understand that? Even though we're dealing with this little section here, if we actually knew what that number was in there, we could put those numbers in there and it would still equal 204. Times our direction. Okay, so 0.2 times 0.2 times 204. Can somebody do that for me, please? V out equals 100 plus, this is essentially, well, 0.02, so it's going to be negative 0.02, which is essentially 0, plus, that was a negative, what do we have? Minus 8.16. Okay, So with the negative 0.02, it would be minus 8.18. So immediately, as soon as the controller sees this ramp rate happen, it doesn't need to see the entire ramp rate. It sees it as soon as it happens. And it says, whoa, we're going to jump down 8.6. We're going to drop down to 91.84, right? Now, we're going to calculate out to see what it's going to be at 100%. Okay. What I need to do is go up. Okay. So V out equals 100 plus. Now, when our process variable ends up being at 100%, our new error is 100, right? Do you understand that? When we get out to half a minute, our process variable has ramped all the way up to 100. That means our error is process variable minus the set point, and that's going to be 100 minus 0, which is going to be an error of 100. So, we have V out equals 0.2, that's our process, our proportional gain, times our error of 100, times our direction of -1, plus our derivative, which equals 0.2 times 0.2 times, and it's still the same ramp rate of 204 times -1. Well, because we already know that 0.2 times 0.2 times 204 times 1 equals negative 8.16 plus 0.2 times 100 equals 20, and we have times -1, which equals -20, plus 100. So we have 100 plus -20 plus -8. So V out equals 71.84. And I do believe that I put 91.84. Good. So now, that was 71.84. So now, at time, and it's actually supposed to be 0.49 minutes, is what it's actually supposed to be, because we went 29.4 seconds. It comes to 71, so that would be about there. 71.84% output. So you see how it continues down. Now that's all proportional that is actually trending down. Watch this. Watch what happens to the derivative as soon as this gets to 100 and it stops at 100. Well, once it stops at 100, is there any more ramp rate?
No.
It stopped. And when it stopped, that means the ramp rate stopped. So what's going to happen to the derivative is the derivative is going to go to 0. And then we're left with the proportional output. Okay? So now, our process variable went from 0 to 100. But now, the ramp rate has stopped because it can't get more output. So now what's going to happen is we're going to go V out equals 100 plus, and it's going to be the same thing. We still have that error, proportional gain times your error of 100 times your direction, plus, now we have our proportional gain times our derivative gain times, we have a ramp rate of 0 times our direction. Well, that makes that whole thing 0. So now we have 100 plus minus 20. So our V out equals 80. So what's going to happen is this is now going to jump up to 80% output. Okay? Now, you would notice that if you did not have derivative, you would have went from 100 down to 80 with proportional gain only. But derivative added 8.16, a negative 8.16. And it added that the entire way that the ramp rate was there. Whenever there was a ramp rate, there was that extra minus 8.16. As soon as the ramp rate stopped, this jumped back up to 80. Okay? At any time here, now I should have, wonder if I can just select that one line. That should have been, I should put that as a red color right there. That would have been more easily visible. The red is what it would have been if it was proportional only. The black is what you are going to see in proportional and derivative. The red portion is the proportional, the black portion is the proportional plus the derivative. The derivative was 8.16 the entire time until the ramp rate stopped. Should the process variable, let's just do an imaginary color here. Should the process variable at, let's say, at the middle of our time at 0.25 minutes, should the process variable have leveled off right there? Well, this would have jumped back up. Your output would have, your derivative would have stopped, and it would have been proportional only for the rest of the time. Okay? We're going to see that. We're going to set up a controller, and we're going to do it. And we're going to do several labs to basically slow down derivative. Because what derivative is trying to do is anytime that you have your set point is here. Your process variable, if it's going along and it's happy, your output, so this would be your process variable, and this would be your output. If your output is coming along because your process variable is just going along steady, this is your proportional band, or your proportional gain, right? Your proportional gain is giving you this output. As soon as you get a ramp of any kind, if this is in reverse acting, it's going to jump, not just proportionally, but derivatively. Derivative means that it's going to the slope. So it's like if in a car, when you're driving along, and all of a sudden your vehicle feels that you're going up a hill, it doesn't feel that you're going up a hill. It sees that there is now a ramp rate showing that your speed is trending down, and that's why it all of a sudden kicks down a gear and starts to rev up your engine. That's not proportional, that's derivative. The proportional would be just give it a little bit more, give it a little bit more fuel, a little bit more. So, what we're going to do is we're going to take a look at it on there, on the actual controller. And through a series of different parameters, you're going to see how it's going to react when you change your proportional versus changing your derivative. Because your proportional is going to affect your derivative. As we can see here, your proportional, you have to multiply your proportional by your derivative. So when you change your proportional, you change your derivative. Right? This way?
Yes, perfect.
Okay.
Sorry. So with derivative, it's looking to match the slope, or it's looking to create a slope where the two slopes will meet together at your set point, ideally?
It's not going to match your slope. See, the proportion, if I just move this down a little, your derivative gain and along with your proportional gain are going to dictate what, how it's going to react to that ramp rate. Okay? If you have a ramp rate that is a little ramp rate, you might have your derivative really ramping up. You might only have it ramping up a little. It depends on how you want it to react. But the fact is it does react to the ramp rate. And so we can change how it reacts by changing our proportional gain or our derivative gain. The error over time is the ramp rate. We can't change that. And the time and the direction is the direction it's going in. So we're not changing the direction. We're not changing the time or the error. We're only changing the proportional gain or the derivative gain to change how it's going to react to a different ramp rate. Okay? Now let's see how that works out on the controller. Now we said, keep this in mind right here. We said it's going to go from 100 to 91, 92 instantaneously, almost instantaneously. Okay? And then over the course of 30 seconds, it's going to get down to 71.84. And as soon as this goes above 100, it's going to jump back up to 80. Okay? So let's check that out and let's see if I'm right. So here we have the controller that we're going to control, and we're going to see the derivative action. This is our controller right here. The reason why we have this controller is simply to inject a very crisp, very clean ramp rate from 0 to 100 into the input of this controller. Now, what is that ramp rate going to be? It's going to go from, this controller is going to go from 0 to 100% in 29.4 seconds. Okay, so we're also going to time that. Now, granted, I understand, and hopefully everybody here understands that, excuse me, that this might not actually happen in 29.4 seconds, and that's a problem with the controller, not a problem with our math. So it might be off by a hair, but it'll be super, super close. Excuse me. Now, what I'm going to do is I'm going to make a minus 20% error on this controller, which as soon as I do that, it's going to inject that ramp rate into this controller. And this controller is going to go, it has a set point right now of 0, as we saw earlier on the board, and we are going to watch the valve output. So the output is going to go from 100, instantaneously drop down to 91.84. Over the course of half of a minute, it's going to go down to 71.84, and then it's going to, as soon as the first controller ends up going above 100, the ramp rate will stop, and then this controller will go back up to 80. So let's try that. We are in automatic mode. Our valve is at 100%. I got my timer ready. I'm going to create the air to the first controller, which is going to give us the ramp rate. So I'm going to hit these try to hit them at the same time. So we notice that it dropped down almost instantaneously to 91. Now, I know it wasn't exactly instantaneous, okay, but it was very close. Now we're watching it. We're at almost 20 seconds. We're down to 82. We're going to see it get down to very close to 71, and we're going to see that. We're at 77, and we're at 30 seconds now. And I do believe it goes to about 36 seconds. So now we've hit our maximum output, and you see it drop down to 73, which is very close. And now it's back up to 79.3. extremely close to 80. Okay? So you see that? We not only proved the math, but we proved it in reality. We proved it right here.